What's up? I'm Vin, and today I want to go through the June 2022 Geometry Regions Parts 2, 3, and 4. So let's get started. Question 25 here is about the Leaning Tower of Pisa, and the diagram really just tells us everything we need to know, and we need to determine and state the slant height x, which is the low side of the tower to the nearest hundredth of a foot. So this is all trigonometry here, and you want to think SOHCAHTOA, because that's going to help you choose the appropriate trig function. So we know this 86.03 degree angle, and just know the height here is the side opposite of that angle. So this is the opposite side, and we're looking for x, which is the hypotenuse, which I'll abbreviate with HYP here. So then when you have opposite and hypotenuse bouncing around in your head, you should be thinking of the sine function here. So what we would have is we'd have sine of, and I'll write it over here, we have sine of 86.03 degrees is equal to the ratio of the side opposite of the angle, which is 183.27, over x, the hypotenuse. So now we just have to do a little bit of algebra here. We could cross multiply, and we'll have x times sine 86.03 degrees equals 183.27. And now to solve for x, just divide both sides by sine of 86.03 degrees. And the rest of this we just type right in the calculator. So let's go ahead and type this in, and notice we're in degree mode here. What we have is we have 183.27, and we're dividing by sine of 86.03. And what we have here, 183.71. And notice I said x equals 183.71. We stopped here because it says to round to the nearest hundredth of a foot. So x is 183.71 feet, and that's our answer to 25. Question 26 has a lot going on, but what we want to do is we want to determine and state the measure of angle B, which is this angle over here in this corner. So we have the measure of angle B. We're looking for this angle over here. And one thing to be mindful of is that angle B intercepts these two arcs here. It intercepts arc AD, and it intercepts arc DC. So now we have to use the rest of the given information here. We're told the ratio of these arcs is in the ratio of 2 to 3 to 5 to 5. So what I like to do for questions like this is CD is written first, and that has a 2. So what we're going to do is we're just going to write a 2x here, and then what we have is we have DA has 3 parts of the ratio, so that's going to get a 3x. And then what we have after that, the rest of the pieces here, we have 5x and we have 5x. And just know the measure of all of the arcs of a circle add up to 360 degrees. So if we add 3x plus 2x is 5x, plus 5x is 10x, plus another 5x is 15x. 15x has to equal 360. And now we're going to divide both sides by 15. And what this tells us here, once we divide, we have x equals, and let's just see, we have 2, 6 here. So x is going to be equal to 24. And with that, what that's going to tell us here, it's going to tell us the measure of each of these arcs. So now 3 times x, the measure of this arc here, this arc is going to be 3 times 24 is 72. So we have 72 degrees here. And then 2 times x, 2 times 24, this arc here is going to be 48 degrees. And now the idea is that the measure of angle B is an inscribed angle, so it's equal to half the measure of the intercepted arc. So that tells us we have the measure of angle B is going to be equal to half of the sum of 72 and 48. So we're just going to take half of that, and that's going to work out to 120 degrees, and we're dividing that by 2. So the measure of angle B is 60 degrees. So question 27, we want to determine and state the volume of the cone in terms of pi. So what we have to know, the volume of a cone is 1/3 pi r squared times h. So what we're told here is the diameter. So there's one little trap set for us. If the diameter is 10 units, then the radius is going to be 5 units long. And we're told the slant height here, so we have to be careful not to plug that into this equation. What we need to find is the actual height of the cone, which goes from the top here at that point straight down to the center like this. So the concept is that in a right circular cone, what we have is cross sections are going to make right triangles. So we want to focus in on one of these right triangles here, and notice once again the radius is equal to 5, the hypotenuse is equal to 13, so the measure of the height is going to be 12. Now the way that I know this is that this is a 5, 12, 13 Pythagorean triple. If you didn't know the height here, what you could do is say 5 squared plus h squared equals 13 squared, and then h squared you could say is 13 squared minus 5 squared. So then h squared would equal 169 minus 25 is 144, and that would tell you h is equal to 12. Or if you know your Pythagorean triples, you just get that right away. So now that we know the height, what we're going to do is we're going to find the volume. It's going to be 1/3 pi times the radius squared, so we have 5 squared, times the height, which is 12. And we're writing our answer in terms of pi, so we could just simplify this. This is 1/3 times pi times, we have 25, and then we have 12 here tacked on at the end. So now we just have to simplify everything. 1/3 of 12 is equal to 4, and then 4 times 25 is 100. So this is going to work out to 100 pi, and that's the volume of our cone. So for this question here, we have a diagram of two parallelograms, and we're told here that to map this parallelogram onto this one, we're doing a reflection over line L. Okay, so that's really important information here. And we want to use the properties of rigid motions to explain why parallelogram EFGH is congruent to parallelogram IJKH. Well, the property of rigid motions here is that a reflection, which is a rigid motion, preserves distance and it preserves angles between the lines. So what that tells us is that if distance and angles are preserved, then that means this parallelogram here is going to be congruent to this parallelogram. Now, just in case you haven't seen these symbols before, the 3 dots mean therefore. Question 29, Izzy is making clay pendants in the shape of a solid hemisphere. And we have the radius of each hemisphere is 2.8 centimeters. We want to know how much clay to the nearest cubic centimeter does Izzy need to make 100 pendants. Well, the most important thing we need to know here is the formula for the volume of a hemisphere. The volume of a full sphere is 4/3 pi r cubed. So if we want the volume of a hemisphere, we just divide this by 2. And we could leave it like this, but I'll write it as 2/1, and we'll do a little bit of algebra here. Just know anytime you divide fractions, just do keep, change, flip. We keep the top, change the operation from division to multiplication, and we flip the bottom. And then 4/2 simplifies to 2. So this would be the same thing as 2/3 pi r cubed. But now what we want is, we want to know how much clay to make 100 pendants. So now we're going to do 100 times 2/3 pi times the radius cubed. And we said that the radius cubed was equal to the radius is equal to 2.8 centimeters. So we have 2.8 centimeters like this. So notice our units here is cubic centimeters. When we do centimeters to the 3rd power, that's going to give us cubic centimeters at the end. And we're rounding to the nearest whole number. So let's type this in the calculator. So we have 100 times, and then we had 2/3, and then we had pi times the radius cubed, which was 2.8 to the 3rd power. So we have 2.8 now going to the 3rd power like this. Okay, so once again, 100 times 2/3 pi r cubed. And we're rounding to the nearest whole number. So we're going to round to 4598, 4,598. So once again, our answer rounded to the nearest whole number is 4,598, and the units are cubic centimeters. So this question here, we have to know the equation of a circle, which is x minus h squared plus y minus k squared is equal to r squared. And we want to find the center and radius of the circle, and here's the equation for it. So the trick with these questions is you have to know how to do completing the square. So what I would do here is I'm going to rewrite this equation as x squared plus 6x. I'm going to leave a space here, and then I'm going to write plus y squared, and we have equals 6y plus 63. And what I'm going to do first is I'm going to get the 6y on this side, because what you want to do for these type of questions is get the x's and y's on one side and the constants on the other side. So now what we have is x squared plus 6x. I'm going to leave a space here, and then we have plus y squared minus 6y. I'm going to leave another space, and I'm going to write equals 63. Now the spaces are there because now we have to do a technique called completing the square. And the trick with completing the square is you have to think of ax squared plus bx plus c. And what we say is we take half of the b term. The b term refers to the coefficient of x or y. So in this case here, look, our b term is 6. So I take half of that, and then I square it. And 3 squared is equal to 9. And that's what I would add to both sides like this. Now, the reason why we call this completing the square is now this trinomial is a perfect square trinomial. So we're turning it into a perfect square. Now we do the same thing for the second expression. The b term for the y equation, or the y expression, is -6. And when we take half of -6 and square it, we also get +9, because -3 squared is 9. So we're going to add 9 to both sides again. So now let's write out, what did we get here? Well, now we have x squared plus 6x plus 9, and now we have plus y squared minus 6y plus 9 equals 63 plus 9 plus 9 is going to give us 81. And now we could factor this. So we're going to factor each of these. This is going to factor to x plus 3 squared. And we're going to have plus, the second part factors to y minus 3 squared. And the right side I'm going to write as 9 squared, because now you could see that it matches the general equation of a circle. So the trick to identifying the center is that you just have to take the reverse of the number in front of x and y. So notice the number in front of x is +3, so then I write a -3. And I have a -3 here, so my y coordinate of the center is going to be +3. And now the radius here, we could say r equals, and remember, it's a common trap here. Don't say r equals 81. The radius is being squared. So r is equal to 9. And here's our solution to question 30. So question 31, we want to construct a line parallel to line AB to go through point C. So for this type of construction, what you could do is you could just introduce a random line, and the random line has to go through the original line AB, and it has to pass through point C. So I'm just going to move this over a little bit so it's precise here, and it goes right through the center of that point. And now let's say I just label this over here. I call this point P. So then what I want to do is this angle CPB, I want to copy this angle, but I want to copy it over here at point C. So what we do is we take the compass, and I'm going to do my best to place it directly on this vertex here. But I did draw that a little bit big. So let's just say that's about where it needs to be here. And what I'm going to do is I'm going to swing an arc so that it hits line AB, and it hits that new line that I just drew in originally like this. And then what we do is we move the compass over to point C, and we're going to swing that arc once again. I'm going to swing it here. And you can kind of imagine where that parallel line is going to go. So just make sure the arc definitely reaches it. So we're going to swing here, and then I'm going to move this over here, and I'll swing it again like this. Okay, so now that we have this, I could go ahead and throw in some more labels. I'm going to call this, let's say, point Q. We'll call this point R. And then this, I'm just going to call point S for now. And the next thing I need to do is I need to shift the measure of the compass to measure the distance between R and Q, because that's one of the last steps to copying an angle here. So once again, here is the measure of the angle. This looks about right. So now I'm going to swing an arc just to show that I measured it exactly. And now I'm going to move this over to point S. And once again, I'm doing my best to be as precise as possible, so this comes out nice. And now here's the second arc, and there's that last point of intersection that we need. So now I'm going to call this point here, let's say I call it point T, so that now when we draw our line in, our line that goes through C and T is going to be parallel to AB. And this doesn't have to be 100% exact, right? The tick marks and everything from your construction is what's going to give you the full credit here. But now I'm going to go ahead and draw my line like this, and we could say that these two lines here are in fact parallel because we follow the construction process. If I want to write a formal statement at the bottom, I could do that too. I could say our original line AB is parallel to our new line, which we'll name CT. Question 32, we have a projector on a ceiling, and we have all these measurements here, and what we want to do is find the measure of angle theta to the nearest tenth of a degree. So for this question here, what we have to do is we have to make use of the fact that there were two right triangles going on in this diagram. The first one I'm going to highlight here in red. So we have this right triangle. And then the next one I want to look at is the big right triangle, which captures all of this here. So this one that goes from here to here to here like this. Okay, so this triangle. And what I'm going to do is I'm going to throw in two more angles. I'm going to call this angle here, I'm going to call this angle beta. And then this little angle in here we could call alpha. And the idea is that theta plus alpha equals beta. So if I want to find out what theta is, I could do the whole angle beta minus that small angle alpha. So now what we'll do is we'll focus on the two right triangles separately. So this right triangle here using just alpha would be built by looking at this side, which is 3.74 meters long, and this side, which is 0.41 meters long. So that's the small one. Now the big triangle here, I'm going to draw out like this. To find these dimensions, well, for one, this entire length is not going to change, the 3.74. but this height is going to change here. I would do 1.17 plus 0.41. And if you add those together, what you're going to get 1.58 meters when I add these two together. So now this big triangle in blue gives us angle beta. So what we said is that the measure of angle theta, we could just now write it all out. The measure of angle theta is equal to the measure of angle beta, that's the big angle, minus the measure of angle alpha, which is the small angle here. So now we just have to come up with an expression for the measure of angle beta here, and we're going to use SOHCAHTOA. So now if we want to find the measure of angle beta, notice we have the side opposite and adjacent, so we're going to use tangent here. So we're going to do tangent inverse because we want the angle, tangent inverse of 1.58 over 3.74. And now we're going to subtract the measure of angle alpha would be tangent inverse of, we'd have 0.41 over 3.74. Now, just know a common mistake with these questions is that people plug these ratios right into the tangent function. But since we want the angle and we're given the ratio, we're going to use tangent inverse. Because remember, tangent inverse, sine inverse, cosine inverse tells you angles. Sine, cosine, and tangent of an angle gives you the ratio. So now the rest is all calculator work. So let's type this in. We have second tan for tangent inverse, and we have 1.58, and we're dividing by 3.74. Now we close that out, and we're going to subtract the measure of the other angle. We said we're going to use tangent inverse of 0.41, and we're dividing by 3.74. So now we just press enter here, and to the nearest tenth of a degree, it's going to be 16.6. So our final answer to 32 is 16.6 degrees. Question 33, the dreaded triangle proof. Now for these questions, it's all about strategy. Our ultimate goal is to prove that segment PT, which is over here, is congruent to segment RU. So anytime you hear that phrase like two line segments are congruent, there's a few routes you could go, but a common one that pops into my head is CPCTC. The way I remember this, corresponding parts of congruent triangles are congruent. There's funny ways to remember it, like constipated people can't take craps. But what you want to do if you're going to use this strategy is prove that two triangles are congruent. So I would want to prove that this triangle is congruent to this triangle. So now I think about what they told us. They told us QT is perpendicular to PS, which means that these angles here are right angles. We're also told that SU is perpendicular to QR, which means these two angles are going to be 90 degrees. They're going to be right angles here. So right away, it's like, all right, these two triangles have one pair of congruent angles. They told us this is a parallelogram, the big shape, PQRS is a parallelogram, which means that this angle here is going to be congruent to this angle here because opposite angles of a parallelogram are congruent. And then now here's the last piece that we're going to need. RS is congruent to QP because opposite sides of a parallelogram are congruent. So notice we have angle side congruency. So these are just some of the things that are bouncing around in my head, and now we write out the proof. So we'll make two columns for statements and reasons. Now the easiest statement to write, which gets you no points, is the givens. So now that the obvious is out of the way, we'll just start writing down some of the other stuff we observed. So what we could say here is because we already established we have a parallelogram, we could say that RS is congruent to PQ. And our reasoning for this, why are these two segments congruent? Well, we could say opposite sides of a parallelogram are congruent. Okay, and on the geometry regions, you could abbreviate with symbols like this. That's more than okay. So the next thing we said to point out here, we're trying to establish angle side congruency. So far what we established is a pair of sides are congruent. So now we could state that angle R in that corner here is congruent to angle P in this corner. And how do we know those two angles are the same? Well, opposite angles of a parallelogram are congruent. So now so far what we've established is a pair of angles and a pair of sides. So now we just have to establish the last pair of angles. The right angles are congruent. And this could be annoying to write out. When you're writing out that right angles are congruent, first you have to establish that they're actually right angles. So what I would say here is that angle RUS So we have angle RUS and angle PTQ. So let's establish that these angles here are right angles. So we have R right angles. And the reason why we know this is true is because perpendicular lines form right angles. And once again, this upside down capital T means perpendicular, and this symbol here, we could just abbreviate angles with that less than looking sign here. But now what we actually have to say, otherwise we'll be in a little bit of trouble here, is we have to say that these two angles are congruent. So once we've established that they're right angles, now we could say that angle RUS is congruent to angle PTQ. And the reasoning behind this is that all right angles are congruent. Well, now we have to think about what we just established, and we established that we have a pair of congruent sides and two pairs of congruent angles. So now we're allowed to say here that these two triangles, and we could just say triangle RUS is going to be congruent to the other triangle PTQ. And the reasoning behind this was already in our thought process, and that's angle, angle, side. So now we're finally ready to prove the thing we were trying to prove. We're going to say that segment PT is congruent to segment RU, and this was once again part of our thought process from the beginning, so we already knew what our reason was going to be, and we're going to say corresponding parts of congruent triangles are congruent, and we could abbreviate it like this. So question 34 here, we have concrete cylinders, and one cylinder is 4 feet tall, so that's the height. The height is 4 feet. We're told the diameter is 12 inches. So right away I see a trap has been set because feet and inches don't match, and the contractor's making 10 of these things. And now here's the next piece of useful information. We have 1 bag of concrete mix makes 2/3 of a cubic foot of concrete. So 1 bag I'm writing equals 2/3 cubic feet like this. And now how does that help us? Well, that tells us the diameter in inches we should express in feet because the bag is modeled in cubic feet. So we're going to turn 12 inches into 1 foot because 12 inches is equal to a foot. And ultimately, we're going to be finding the volume of these cylinders, and the volume of a cylinder is pi r squared h. So notice we need the radius. So the radius is half of the diameter, so that would be 0.5 feet. So this is going to be something important as well as the height. So we're going to need these two in a moment. And now what we have here is the volume of 10 bags would be 10 times, we'd have pi times the radius squared. The radius is 0.5, and that's being squared. And then we're multiplying by the height, which is 4 feet. And now just know the radius squared, I'm going to have feet squared is square feet, times 4 feet would give me cubic feet. So I'm just going to write the cubic feet here because this is the volume of 10 bags. And what we have to be mindful of is if 1 bag is equal to 2/3 of a cubic foot, well, 1 bag makes 2/3 of a cubic foot of concrete, then to express how many bags we're going to need here, we could multiply this by 1 bag per 2/3 cubic feet. Okay, so this is just unit conversion here. If 1 bag gives us 2/3 of a cubic foot, we could multiply this volume here by 1 bag over 2/3 cubic feet. And notice cubic feet over cubic feet cancels. And now what we have to do is just type this into the calculator and then divide it by 2/3. So let's type that in. We have 10 pi. So 10 pi, and then we have 0.5 squared. And then after this, we have times 4. And the last thing we did was divide by, I'm going to put parentheses here, we're dividing by 2/3. And that brings us here, 47.124. Now, one little trap here is we said a moment ago, 47.124, whatever. If we're not careful, we might round down to 47, but we're making concrete fillings. So what we're going to need the extra bag of concrete to make that last cylinder. Okay, we're not going to round down because then we wouldn't have enough concrete. So since this is an actual real world scenario, in this situation here, we would have to round this up to 48 bags because otherwise we wouldn't have enough material to make the last concrete cylinder. So this is going to work out how many bags are we going to need? We're going to need 48 bags of concrete mix to make all the cylinders. So part 4, the final part of this test, we have a coordinate proof here, and we have the vertices of triangle ABC, and we want to prove that this triangle is isosceles. So for questions like this, honestly, all I do is I just do the distance formula on rapid fire mode here. So when I'm thinking of triangle ABC, if I want to prove that this triangle is isosceles, I'm going to find the length of all three sides. So I would start by finding the length of AB. And to find the length of AB, it helps to know the distance formula. The distance formula we could write out here is the difference of x2 and x1 squared, plus we would have y2 minus y1 squared. And we're just going to use that many, many times here. So if I use that here, I would have the square root of, and let's say I start with -7 as my x2. I would have -7 minus -2, and I'm squaring that, plus then I would have -1 minus 4 squared. And it doesn't matter which one you make x2 and x1, but it does matter once you pick one to be x2 that this is y2. So now we go forward with this, and this tells us AB is equal to, and now what we have is -7 minus -2 makes -5, and -5 squared is 25, plus this makes -5, and when we square it, is going to also give us 25. So this gives us the square root of 50, and I'm just going to simplify this. This is radical 25 times radical 2, so this is 5 radical 2. Now I'm just going to do this 2 more times. Next, let's say I want to find the length of AC. So AC, now I'm going to start this process all over again using the distance formula. I'm going to do -3. So under the square root, of course, I'm going to do -3 minus -2 squared, plus I have another -3, and not going to write a comma, -3 minus 4, and this is being squared as well. So now we work this out. There's going to be -3 minus -2 becomes -3 plus 2, which gives us -1 squared, which is 1, plus, and this is -7 squared, which is 49, and check it out, we have square root of 50 again, which is 5 radical 2. So at this stage here, we definitely have an isosceles triangle because these two sides are the same. But just to keep everything consistent here, I'll find the length of segment BC, which is the last side of this triangle. So now we'll let this be our x2 and this be our x1. We're going to do -3 minus -7, and that's being squared, plus we have -3 minus -1. So you have -3 minus -1, and that's being squared. So this is going to become, let's see here, we have 4 squared, which is 16, plus, and this is going to make -2 squared, which is going to make 4. So this is going to work out to root 20, and square root of 20 breaks down to root 4 times root 5, which is 2 radical 5. So you see that third side is different here, but what we can say is that triangle ABC is isosceles because two sides have equal measure. Now, we probably don't have to write all this extra stuff here, but I like to write a little bit more just to be safe. So the next stage of this problem is we want to state the coordinates of this triangle here, the image of the original triangle, and here's the transformation. We're doing a translation 5 units to the right and 5 units down. So for this question here, what I'm thinking is I'm going to take all the x values, and if we're going 5 units to the right, I'm going to be adding 5 to them, and the y values, I'm going to subtract 5 because we're going 5 units down. So that's kind of like the fast way to go through this, but take your time. Don't say 1 plus 1 is 12. Just make sure you do these right. So we got a is -2, 4. So when we transform this to a prime, this is the shortcut in our head. We're adding 5 to the x. So -2 plus 5 is 3. And then I'm subtracting 5 from the y. 4 minus 5 is -1. So that's the first part taken care of. B is -7, -1. So I'm just going to do this carefully. Don't want to make a mistake adding and subtracting. So I'm adding 5 to x, so -7 plus 5 is -2. And when we subtract 5 from y, -1 minus 5 is going to give us -6. And now I'm just going to do this once more. So we've got C is the point -3, -3. And when we transform this here, we're adding 5 to the x. So -3 plus 5 is 2. And then when we subtract 5, -3 minus 5 is giving us -8. So here are the coordinates we need. All right, now for the last part of this question here, and I'm writing the coordinates from before in the corner because we're going to need those again. So what we need to do is we need to prove that this quadrilateral is a rhombus, and this quadrilateral is A prime, C prime, C. So what I'm imagining in my head here is the order of the letters makes a big difference, that if it's going from A to A prime, and this is not drawn to scale, to C prime, and then to C, it's very important that if I do draw something like this on the side, that I label it in this corresponding order, A prime, C prime, C, because that'll tell us for sure what the side lengths are going to be. So now what I'm going to do is if I want to prove this quadrilateral is a rhombus, I'm going to use the distance formula 4 times, and I'm going to find the length of all 4 sides. So here what we could do is, let's say I start with A prime. I could say A prime is equal to, and I'm using the distance formula all over again. So remember, A prime was 3, -1. A was -2, 4. So now I'm going to do the difference of the x values. I'm doing 3 minus -2. So I have 3 minus -2, and make that neater. So 3 minus -2, and that's being squared, plus I'm going to have -1 minus 4, and that's being squared. And now this is going to work out to 5 squared plus -5 squared, which is going to give us square root of 50, and that's going to give us, once again, 5 square root of 2. So that's one side taken care of. So next I could do A prime, C prime. Now for this one here, before we found the length of AC, so I could use properties of rigid motions here, but just to be safe, I'm just going to once again go ahead and do this by brute force. The only one maybe I won't rewrite is when we talk about the length of AC, because that we already found to be 5 root 2. So now A prime, C prime, what we could do here is A prime, C prime, I'm going to use this point, A prime here and C prime here. So I'm going to have 3 minus 2. So let's say I'm calling A prime x2, y2. I have 3 minus 2, the difference of the x values squared, plus, and now I have -1 minus -8. And that's going to be squared as well. So this is going to work out to 1 squared plus 7 squared, which is going to give us square root of 50, which is also giving us 5 root 2. Now AC, so we just found, let's see, A prime, C prime. AC I could just say is equal to 5 root 2 because we already did this work earlier. So that one's taken care of. Now the last one to find would be CC prime. And if we find the length of CC prime, we're going to use the distance formula once more. So we have the square root of, and I could say, let's call this x2, 2 minus -3. And this is being squared plus, and now we have -8 minus -3. And this is being squared. And the beauty of a question like this is if we don't get root 50, you know something got thrown off somewhere, so you could just kind of go back and fix it up. So 2 minus -3 is 5, and 5 squared is 25, plus -8 minus -3 makes -5. So I have 25 plus 25 is root 50, and this is equal to 5 root 2. So I don't even need to use the grid for this. I just imagine the ordering of the letters, and I just use the distance formula 4 times. But now we have enough information to write our conclusion. We can say that this quadrilateral is a rhombus because all 4 sides are equal in measure. Remember, if I'm writing a proof here, I would just make sure to mention in some statement here that you're saying all 4 sides are actually equal in measure, and then use that to write your conclusion.